Okay, so we are talking about group. We define the group. Group is having 4 properties: closure, associativity, existence of identity, and the existence of inverse for every element. Then that algebraic structure along with the operator is called group. Now, it is if the star is that algebraic structure. So, if this is a commutative, then it is called commutative group or abelian group. Okay. Now, suppose today we will talk about the ordering of a group. I mean the order of an element and also the ordering of a group, then the cyclic group. Okay. So, to start with, let G be a group. So, that means what? That means this is a binary operations, this is closure. So, that means A star B belongs to G for all A B belongs to G. This is closure property. Then we have associativity property. This is also true for all A B C. And then we have existence of inverse. There must exist a E such that A star E is E star A is equal to A. This is true for all A, and this we have seen this is unique. There must exist a unique E such that this we have proved in the last class maybe. Now, the inverse is basically for a given A belongs to G, there exists a B which we denote by A prime such that if we operate A with A prime in both the way, this is. So, it is also right inverse, left inverse, and right inverse, left inverse are same. That is the inverse, and this E this is also unique. This is unique. Now, if these 4 properties satisfy, then we say this algebraic structure G along with this operator, binary operator, this structure is from a group. Okay. Now, we talk about ordering of an element. So, the integral power of an element we talk about. Of an element from G. Let A be an element from G, any element. Now, if we suppose A is equal to E, identity element, then if we operate A star A, this will basically E star E. So, this is E. So, E star E all are basically E star E. Okay. But if A is not E, A is not the identity element, then what we do? We keep on, this is the integral power of an element, we keep on apply A with itself. So, like so A is an element, so A star A will also be an element because of closure property. A star A, 3 times we are operating like this, A star A 4 times like this dot. This way we continue. Okay. Now, this is A, we are, so this is continue. So, in general this is A star A, say this is n times. So, this we denote by say A square, A cube, A to the power 4, A to the power n, this one. If our star is in multiplicative sense, this is when the star is multiplicative sense. Multiplicative sense. Then we multiply. Multiply means a into b kind of thing. So, a into a is a square like this. So, this is just a notation, but if the star is additive sense, then this will be written as if star is in the additive sense, this operator, then this will be a, 2a, 3a dot 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 n a. So, this is the additive sense. So, if star is additive sense, but anyway in general we will just this a will mean the a to the power n will mean the a star a n times, and this will be belongs to G because of closure property. So, this is the integral part of a, we keep on applying a with the elements, and by closure property this will be a. Now, we say this is so this is how we define the a to the power n. This is the integral part of the element a to the power n, or in the additive sense n a, if it is, if the star is the additive sense. Okay. So, now we will have some property before we go to the defining the order of an element. Okay. So, first property is a to the power n into means suppose our star is in multiplicative sense, a to the power m is equal to a to the power m plus n. Okay. This is our star. So, this is also star, this is also star, m times n times a. This is quite obvious because this a to the power n is basically a star n times, then we have a to the power m, this is also a star, this is n times and this is m times. Now, if you multiply this, if you operate these two again, and here to the power means we are taking the operation in multiplicative sense, but it could be additive sense also, then it will be a n a plus m a, then it will be m plus n a. Anyway, so now we, if we do the star with these two, then it will be basically a to the power a times a, this is total is this is n times m times, total is m plus n times. So, this is basically a to the power n plus m. Okay. This is just a this one. Now, another result is, suppose a to the power n to the power m. So, this is nothing but a to the power n m. So, this n m are all coming from natural number set, I mean, or it could be integer. So, set of integer, any number, these are any integers. Okay. This could be negative also. Now, this is also can be easily proved, because this is a to the power n m times, each of having n operator n times. So, total is n into m times. So, another result is a to the power n to the power minus 1. This minus means minus 1 means the inverse. So, this is nothing but okay. So, this is what, this is the in. So, what is a to the power n? A to the, so b is equal to a to the power n. This is basically a star a n times. Okay. Now, if you take the inverse of this, this is basically, this is an element. So, this is basically inverse of this a star inverse. Now, this is, we know the result a star b inverse is equal to b inverse a inverse. This is means inverse. It is the multiplicative sense operator. So, that is why it is inverse. That is why it write in this way to the power minus 1. Otherwise, if it is additive sense, then you have to write minus of a to the power n. But anyway, so this is basically if we apply this, and this is true for more than 2 also. So, then it will be A inverse n times. So, this is basically A inverse to the power n. So, this result is true. Okay. So, you can have some more result on this power of an element. This is power because we are telling this is power as we consider this operator as a multiplicative sense. Otherwise, if it is additive sense, instead of a to the power n is multiplicative sense. The star. But if the star is additive sense, then it is Na, additive sense. So, depending on the, but the meaning is a to the power n, meaning is n times we operate A with itself. Same meaning, Na means n times we operate A with itself. Okay. So, now we define ordering of an element. Order of an element. Okay. So, again let G be a group, non-empty group. Is there any empty group? I mean, if G is empty, then there is no element exists there. So, that G be a non-empty group means G is not equal to phi. Okay, and let A be an element from G, any arbitrary element we take. Now, we will talk about ordering of an element. Now, A is, this is the definition. Now, A is said to be finite order, said to be finite order element if there exists a natural number n such that a to the power n is equal to E. E is the identity element from the group. If we so there is only one group, so we can write E G or E. E is okay, because there is just till now you are just G is the group. So, E is the identity element. This is the identity element of the group. Okay. So, if such an n exists, if such natural number finite, if there exists a finite order, if such n exists. So, that means what? That means exists, then we say this is having a finite order, and the order of the group is basically the least n which satisfying this. Okay. And the order of the group, the least n, least positive integer n such that a to the power n is equal to E is called order of the group, is called order of that element, order of A, order of that element. Okay. So, basically is basically the order of an element. A is basically the minimum least element among all n such that a to the power n is E. This is the how we define the order of the element. Why minimum? Because see, we are keep on, say we have an element A. So, we are keep on applying A square, A cube, and suddenly say A to the power 5 is giving us E first time. This is the minimum one. Now, if A to the power 5 is E, then A to the power 10 is also E, because this is basically A to the power 5 square. So, E square E star E. So, any multi, if A to the power n is E, then the A to the power 2n is also E, A to the power 3n is also E. So, these are basically giving us the identity element, this power, but we need to, that is why we need to choose the minimum one. The least one will give, least one is represent as order of an element. Okay. And we denote this by this symbol, or in short we sometimes denote this by order of A, like this. So, here order is 5. If the 5 is the first natural number such that A to the power 5 is E. Order may exist, may not exist. If such n, such finite n exists, finite n is there, then we say order exists, otherwise order is infinity kind of thing. Now, the convention is this is natural number, because convention is A to the power 0 we take to be E. Okay. This is the convention, A to the power 0 is 0 time we are operating with A, we are not operating with A. So, that is the convention we take to be E, because this will, because we know that A to the power m plus n is A to the power n, A to the power m. Now, if you take n to be 0 or m to be 0, so this is 0, so this is 0. Now, this is basically E star A to the power m. So, this is the convention, A to the power 0 is E. Okay. So, that is why we take the from natural number set this order. Okay. So, now we will talk about if such finite n exists, then we call this is the order of an element. Okay. So, now we talk about the, we talk some of the properties of this order of an element. Okay. So, this is the first property. So, again we have a underlying group and A is an element from G. This first theorem is telling us order of A is same as order of A inverse. They both have same order. How to prove this? Is this trivial? Anyway, unless we convince, nothing is trivial. So, how to prove this? So, order of A, suppose n is the order of A. So, n is the minimum element which is giving us A to the power n to be E, the identity element of the group. Now, what we can do here? We can just take inverse of this. A to the power n inverse is equal to E inverse. E inverse we know it is basically E. Now, we have seen this result, this is basically E. So, this is basically E. Now, this is giving us n is the integer which is basically giving us A to the power A inverse to the power n is equal to E. Now, this n could be the order of A inverse, but for that we need to check whether there is any other m which is less than n such that this is E. This is not possible, because if this is happening, then again we take the inverse, then it will give us A to the power m is equal to E, which is not possible, because this is the minimum element from the natural number set such that this is happened. So, this is not possible. So, this is the n is the, so n is the order of this. So, this is the logic, this is the proof. Okay, now, the second one is second property is if the order of A is n, n, and if a to the power m is e, then n must divides m. N must divides m, because this you have to prove. Intuitively, this is because n is the minimum element, minimum integer such that a to the power n is e. So, now if any other integer divides m, then n must divides this. So, how to prove this? Okay, so, we can write this is by the. So, if we want to divide n by m, so n can be written as q m plus r, where r is the remainder 0 less than r less than n minus 1, less than equal to n minus 1 or less than n. Okay. Now, what? Now, we can just write a to the power m. A to the power n is basically a to the power n is basically a to the power q n plus r. Now, here we can just write this as a to the power n to the power q into a to the power r. Now, this we know this is e. So, this implies e is basically equal to this is we know e. So, this is a to the power r. Now, r is less than n and n is the order of the group. So, n must be the minimum one. So, that means this implies r to be 0. Otherwise, if r is not 0, which is less than n, then r could be the order of the element a. So, this implies m is q n. So, this implies n divides m. Okay, this implies m divides n. This is one of the property. Now, the next one is just we will quickly go through some of the properties. These are we can verify easily. Okay, now, this one if we have a order of a group is n, then a square, a cube, this set a to the power n, which is nothing but e. These are basically distinct element in G. These are distinct elements in G. So, that means no two element will be same. That means, if we take, so if you take 2 I and j here, a to the power I, a to the power j, any arbitrary I and j. So, our claim is this is telling that a to the power I should not be equal to a to the power j, okay, where say j is greater than I. Because if they are same, suppose a to the power j is same as a to the power I, then what we can say from here? We can just say a to the power j minus I is basically a to the power 0, which is we know this is e. So, that means, this is basically a j minus I is less than n and j minus I will be a order, but it is order is n. So, this is the argument. So, if n is the order, then if we operate keep on operate a with itself, then up to a to the power n, this will form a distinct set of operation. Now, the next result is this is number 4. Suppose we have an order of n group A, n, then order of a to the power m is basically n by GCD of m comma n. Okay. So, this is also another result, this we are not going to prove now. Okay, now we talk about Zn. Zn star. So, Zn star is basically, we know Zn is basically 0 1 this set. That means, if we take an integer set and if we take a natural number n and if we divide this by n, this is the all possible remainder, sorry, up to n minus 1. For simplicity, we can write 0 1 2 up to n minus 1. Okay. So, now if we just we know this Zn star, this is a group. Okay, now if we take a element 1 and this is a group with E is 0. Now, if you take a element 1, A is equal to 1, then what is the order of this element? Order of this element will be n, because if we take 1 plus 1, it is 2. So, these are all giving the distinct elements. So, 1 plus 1 plus 1 is 3, like this. So, up to 1 plus n times, it is giving us n minus n minus n. So, n means 1. So, n is it is, so n minus 1 time it is this, and n times it is giving us n, which is mod n is 0. Okay. So, this is basically giving us. So, order of an element 1 is basically n. This is an example where the order of an element we have checked is to be n. Okay. So, in the next class we will discuss the cyclic group and the subgroup also. Thank you.